Good morning again. This is Dr. Jingbo Louise Liu. In this lecture, we are going to continue to study alkyne. Particularly, we are going to focus on the different reactions of alkyne. From last class, when you studied alkyne preparation, we learned one important reaction called alkylation. Today, we are going to learn two types of different reactions. One group of reaction is called addition reaction. Another reaction is called oxidation reaction. So you learn hydrogenation reaction, hydration reaction, hydrohalogenation, halogenation, and ozonolysis. In terms of the hydrogenation reaction, you are going to use alkyne to react with your hydrogens in different amount, in different catalyst. You are going to produce alkyne, or you are going to convert alkyne to alkane or alkene, depends on the catalyst. The second type of reaction called hydration reaction. Your alkyne reacted with water, so therefore you are going to produce some compound called enol. Enol is not a stable isomer, so you are going to learn something called enol ketol tautomerization. And then we are going to learn addition of hydrogen halides, you call hydrohalogenation. So this hydrohalogenation of your alkyne, you can have different four possibilities. You can produce just halides, but with alkene as your substrate. And you can also produce dihalides. So in the hydrohalogenation reaction, you also can follow Markov-Nikov's rule and anti-Markov-Nikov's rule. The other reaction is called halogenation reaction. You add in halogens. Also, you can control the amount of halogens. You can produce dihalogens, and you can also produce tetrahalogens from your alkynes. The other reaction is related to the ozonolysis. You are going to use strong oxidizing agent such as ozo, O3 to break down the triple bonds, convert this alkyne to carboxylic based compounds. That's essentially the chemical reactions we are going to study, followed by we are going to discuss each type of reactions one by one. First type of reaction called hydrogenation of alkyne. Alkyne can be reduced to alkane using hydrogen molecules and a transition metal as catalyst. For example, if you have alkyne as general formula, RCCr prime reacted with 2 moles of hydrogen under the platinum, nickel, or rhodium, you can produce alkane. So meaning the double bonded carbons added 2 more hydrogens. For example, if I have 4 methyl 1 hexane reacted with 2 moles of hydrogen molecule, hydrogen gas. Under nickel catalyst, we are going to produce 3 methyl hexane. So this reaction again need 2 moles of hydrogen gas, and you also need to use metal catalyst. So followed by, we are going to move on to the geometry. So this hydrogenation actually is a stereoselective reaction. Most of the metal catalyzed hydrogenation is a syn addition process. If you have the alkyne reacted with 1 mole of hydrogen, you are under catalyst, you are going to produce a cis alkene. This double bonded carbon will further react with hydrogens and the catalyst again to produce alkane. Due to the single carbon bond can be rotated, so therefore I prefer to produce a trans product to eliminate the steric hindrance Anyway, in this first step, when you produce this alkene, cis product will be the dominating product for you. Another types of hydrogenation reaction is carried on under Landler's catalyst. This Landler's catalyst is a partially deactivated catalyst, so which was developed for a partial hydrogenation of alkyne to alkene. You particularly want to convert triple bonds to double bonds. You use this partially deactivated catalyst, such as you composed of the palladium in the calcium carbonate under lead acetate and quinolines. So in this case, you convert your triple bond to a double bond. This is one example. Second example, you have di-substituted alkyne, such as you have this 5-dikine. So you are going to react it with a hydrogen under Landler catalyst. So you are going to produce a cis 5-dikane. You produce alkene from your alkyne by using a Landler catalyst. Another important reaction is convert this alkyne to alkene using metal ammonia reduction. If you place or you dissolve your group 1 metal, such as sodium, in liquid ammonia, this will be a very strong base. This strong base can reduce alkyne to a trans alkene exclusively, different from your cis addition. So if you're adding hydrogen 1 moles by using catalyst, Landler catalyst, you produce cis alkene based on the syn addition. If I want to produce trans product, how you are going to do this? The trans product, the trans reaction based on converting alkyne to alkene, triple bond to double bond. You are going to use alkaline metals, which is dissolved in liquid ammonia. This strong base will reduce alkyne to trans alkene. For example, if you have 3 hexane under sodium alkaline metal from your group 1, which is dissolved in liquid ammonia, you are going to produce a trans hexane. So trans 2 larger 2 leg group will be located in the opposite side of your carbon double bond. In this reaction, you are going to have a very important intermediate, which is called a Vanno radical. So this radical, this one of the carbon which is going to subjected to the radical formation. So this radical, you call them Vanno radical. Vanno radical prefers to trans conformation. The reason is you want to decrease the steric hindrance. The trans conformation is preferred, even though you can form the cis conformation. Due to the steric hindrance, you want to form a trans. This from Z configuration to E configuration actually is converted very rapidly because the trans or E configuration is more stabilized. This ammonia metal reduction has 4 steps in terms of the mechanism. Sodium atoms dissolved in liquid ammonia is dissociated into the sodium ions, which solvated by the ammonia. You form a sodium positively charged ions solvated by ammonia. Your electron, so sodium dissociated to the sodium cation, and you are going to lose the electron. That electron is going to be also solvated by ammonia. The solvated electrons are represented in the E negative in parentheses Am, represent ammonia solvated electrons. In this reduction reaction of your alkyne using metal ammonia, you are going to go through 4 major steps. The first step called electron configuration, second proton transfer, followed by the second solvated electron transfer, followed by another proton transfer. You have electron transfer, proton transfer, electron transfer, proton transfer again. First step, if you have your alkyne, this triple bonded carbon, they are going to subject it to the homolysis bond cleavage, meaning one of the pi bonds is going to subject it to the homolytic bond cleavage. One electron is going to be retained by one carbon. The second electron retained by another carbon. This carbon on your right-hand side carbon, let me call it beta carbon. This beta carbon will be accepted the solvated electron by ammonia. Ammonia solvated electron going to form a pair with the single electron. Therefore, you form this negatively charged radical. This negatively charged radical obviously is not stable. The anion radical is going to subject to the proton transfer. Negatively charged carbon is going to be attracted to your hydrogen, which is from your ammonia. The nitrogen bonded hydrogen will be attracted by this negatively charged carbon to form another radical. This radical you call the alkyne radical. This radical composed of a carbon double bond and also an unpaired electron in carbon. And then this ammonia becomes to imide. This imide negative is also going to be involved in your further reaction as your catalyst. And then you have sodium dissociated into electrons and sodium cation. This solvated electrons coming from your sodium dissociation again is going to be paired with your unpaired electron from carbon. This radical, anion radical, this alkyne radical. This alkyne radical has a carbon with unpaired electron. So this carbon will be paired with your solvated electron. This is again, both electron transfer are fast step. So you are going to form another alkyne radical, negatively charged anion. This alkyne anion is going to be formed. Again, this negatively charged carbon is going to be attracted to the hydrogen from your ammonia. So hydrogen is going to be bonding with this carbon with the negative charge. You form an alkene, and then you are also produce imide negative ions. This is a four different steps, but mainly related to the transfer of your electron and transfer your proton. Your electron is resulted from the sodium dissociation into the cation ion and the electrons. Both sodium cation ion and the electrons are solvated by ammonia. And your proton has been transferred from your ammonia, so hydrogen bonded with your nitrogen in your ammonia will be subjected to the transfer to the alkyne radical to form the alkyne anion, and then further to alkene. So that's 4 major steps. The second types of reaction of your alkyne will be addition of hydrogen halides. Your hydrogen halides can be added by 1 mole or 2 moles. If you're adding only 1 mole of hydrogen halides, this reaction under regular condition, you are going to follow Markov-Nikov's rule to produce a bromoalkene. So triple bond becomes double bond, and your bromide, for example, is going to be added to the carbon with fewer hydrogens. So hydrogen added to the carbon with more hydrogens, you form this 2-bromohexene. If you have 2 moles of these halides, 2 2 moles of halides, you can produce dihalides. About this mechanism of addition of halides through hydrohalogenation is briefly showing you over this part. So again, in your alkene, so this triple bond meaning more electron density. So that triple bond is going to be attracted to the proton from hydrogen halides. Therefore, this halogen becomes halide negatively charged ions. So proton bonded with the carbon double bonds, causing a carbocation formation. This carbocation actually is alkynyl carbocation. This is not stable. Negative positive ions, they are going to react to produce, we call the this vinyl cation is going to produce alkynyl halides. This is an alkene. Bromo reduced, bromo substituted alkene. You call the alkynyl halides. And the kinetics about this reaction can be briefly represented by the rate equals to the reaction rate constant multiplied by the concentration of your alkyne and the concentration of your hydrogen halides to the power 2. This reaction suggested to be the third order reaction. The reaction order supposed to be number 3. So involved in 2 halides reaction. And also you can add in excess hydrogen halides. As we mentioned, you form this bromohexene can be further adding halides. You are going to follow Markov-Nikov's rule to produce germinal dihalides, meaning both halogens will be added to the same carbon. If you're using a different mechanism, such as under peroxide, go through the radical addition, you are going to have a different reaction. So that one will be following anti-Markov-Nikov's rule. So the Markov-Nikov's rule product, so you are going to produce this dihalides. Anti-Markov-Nikov's rule, you are going to produce bromo replace the substituted hexene. That bromo will be added to the terminal carbon. That's called anti-Markov-Nikov's rule. Even though this carbon you have 1 hydrogen, the second carbon you have 0 hydrogen. However, when you produce the adding the hydrogen halides under peroxides, this is going to initiate the radical addition of hydrogen halides. That's about the hydrohalogenation reaction. The third type of reaction we call the hydration reaction. If you are adding water into the alkyne, hydration reaction will occur. Hydration of your alkyne will yield a special alcohol. This alcohol is called enol. You have an alkene. This alkene double bonded carbon connected to OH hydroxyl group. Enol has an OH group attached to the alkene carbon double bonded compounds. This enol was found not stable. It's going to be tautomerized into the ketones. The enol rapidly isomerizes to the keto form. This reaction occurs rapidly. The forward reaction is more favorable. If you reach the equilibrium, that equilibrium is considered keto-enol tautomerism. The two of these enol and ketone, they are called tautomers. The tautomers are the constitutional isomers. They are different because of the different connectivity, but they have the same molecular formula. These two tautomers can be equilibrated by migration of one atom or one group. In this case, your hydrogen atom is going to be migrated from your oxygen to this double bonded carbon. So you consider hydrogen atom migration. help you to convert enol to ketol. This procedure is called tautomerization. This equilibrium is called ketol-enol tautomerism. That's something special for this hydration reaction. Before in your hydration reaction of your alkene, you simply produce alcohol. In this case, you are going to eventually to produce a ketone. So this enol ketol tautomerization has subject to two different progresses. The first one is protonation. Second one, deprotonation. Protonation meaning you have your enol. Your enol is going to be enol has a double bond. Double bond is going to be attracted to the proton from your hydronium. So what happened? This hydronium becomes to water, losing a proton. The proton is going to be bonded to, let me call this a beta carbon, bonded to this beta carbon. So you essentially form a positively charged conjugate acid of your enol. This form is a conjugate acid of this enol. So this compound, all these positively charged ions, you have positive charge. Obviously, it won't be stable. What's going to happen? This proton bonded with oxygen is going to subject it to the shift. So what's the shift? The shift will be this way. So this oxygen, hydrogen, these two, they are isomers. These two, they are isomers. Actually, I personally prefer this one as our isomers because your oxygen is not, they are the resonance forms. So the oxygen is not preferable to be positively charged. For my case, I personally prefer the B form, but lots of cases we use this A format, the resonance structure of A as our deprotonation. And then your oxygen bonded with this hydrogen is going to be subjected to the bond cleavage. So two electrons going to be moving to the oxygen. So you have a lone pair, and this positive charge along with this hydrogen proton is going to be bonded with your water to form a hydronium. So this molecule becomes your ketone. So there's two major steps, protonation and deprotonation during the ketol-enol tautomerization. For example, I have the hydration of some alkyne. So generally speaking, you just produce your ketol form. Ketol form is more stable. If I have my octine, so I have my octine, so 1, 2, 3, 4, 5, totally 8 different carbons. The triple bond located in the number 3, number 4 carbons, you call 4-octine. So reacted with water under acidic condition using mercury sulfate and basic and acidic solution. So this catalyst is going to allow you to produce 4-octanol. So you form a ketol form. So what happens? Just this carbon double bond, carbon triple bond becomes carbon oxygen double bond. Another reaction is this 1-octine. 1-octine is going to allow the second carbon to be bonded with your oxygen. You form a you are going to form a Markov-Nikov's rule. You are not going to produce this terminal carbon bonded with oxygen. So that's not going to be produced. Not going to form aldehyde. You form ketones. So again, you must have sulfuric acid, strong acid, and mercury sulfate as your catalyst. You convert alkyne to ketone forms. So this is about the hydration reaction. Halogenation reaction of your alkyne, you also can have two possibilities. You can react it with 1 moles, so you produce dihalides, or you act with your alkyne reacted with 2 moles of halogens, you are going to produce tetrahaloalkane, or you form tetrahalides. So for example, I have my propine reacted with 2 moles of chlorine. you are going to form 1122 1122 1122 tetrachloropropane. So that's about the chemical reactions. If you are going to produce some other types of reaction, you want to produce an anti-dihaloalkane. You want to produce alkane, you can simply react it only with 1 mole of your bromide. So you are going to produce this formula. So you have a 3,4,3,4 dibromo 3-hexane. So this is another different types of reaction. So you call the anti-dihalogenation of your alkyne. How about some applications about your alkyne? If I'm going to produce some compounds of the alkyne, how you are going to predict it? You also can go through the ozonolysis about your alkyne. This ozonolysis is called the oxidation reaction of your triple bonds. Ozonolysis will result in the alkyne bond cleavage. This triple bond will be break up. The alkyne carbons are going to be transformed into carboxylic acid carbon. Again, you break up this carbon on your left hand side. This carbon, the alkyne carbon, triple bonded carbon, will becomes to carboxylic COOH. This group is called the carboxylic group. On the other hand, the right hand side, this carbon also going to form this carboxylic compounds. Carboxylic acid carbon, alkyne carbon will be transformed. I should say alkyne subject to the ozonolysis will be resulted in different carboxylic acid carbons. So the end carbon of your terminal alkyne is going to become the end carbon of this terminal alkyne is going to become the carbonic acid. The carbonic acid further can be dissociated into carbon dioxide and water. For example, if I have this 1-hexane, so number 1, number 2 carbon, you are going to subject to the bond cleavage. It's called ozonolysis. Under O3 as your catalyst, also oxidizing agent, and then in water. What's going to happen? This second carbon becomes COOH. This one is called pantanoic acid. Pantanoic acid, and the second part, this terminal carbon, becomes carbonic acid. Carbonic acid is H2CO3. Further can be dissociated into your carbon dioxide and water. The very last topic is related to application of alkyne in your synthesis, such as you are going to use the retrosynthesis to produce, say, epoxide. If I'm giving you one of the compound called acetylene, I'm aiming you are going to use primary bromide to further produce this epoxide. So what's your plan? So how you are going to do this? So you are going to do some thinking from this epoxide. This is what I want to do. So here is our example. You are going to give 2 reactants. One is ethyl bromide. Second one is your acetylene. That's your resources of your carbon. I want you to produce 1,2-epoxy butane. This is your product. What's your plan? You are going to use retrosynthesis method. So this epoxide possibly is resulted from alkene, carbon triple bond. There will be butane. How do you produce butane? Butane you can react it with alkyne, butane. Butane reacted with only 1 more hydrogen, you convert it to butane. How do you produce this full numbered hydrocarbons with a terminal carbon triple bond. This is a monosubstituted alkyne. How you are going to do this? You may thinking of the alkylation. If I give you methyl bromide, meaning you have two carbons, I also give you acetylene. This acetylene, you may thinking about acetylide. Where the acetylide comes from must come from acetylene. Acetylene considered as acid. You must have a very strong base. The very strong base can be sodium dissolved in ammonia, liquid ammonia. So the alkaline metal dissolved in ammonia, so give you this sodium amide. Under this reaction, you are going to break up these triple bonds. So one of the triple bonds is going to be involved in, or you can say this proton is going to be subjected to removal. So you donate a proton from your acetylene and form a sodium salt, and then you are having this negatively charged carbon you call the acetylide. Acetylide reacted with your methyl bromide. This carbon bonded with this triple bonded carbon. So you are going to increase the number of the carbon chain through alkylation reaction. And then you are going to use a Lindler catalyst, adding 1 mole hydrogen. So you produce, you convert alkyne to alkene, or you can use that sodium ammonia reaction. So subject to the 4 different steps: electron transfer, proton transfer, electron transfer again, proton transfer again, you produce alkyne. This alkyne under oxidizing agent, you are going to produce an epoxide. That's what you are going to think. Again, this method is called retrosynthesis. Retrosynthesis gives you a very good outline about how to produce a compound starting from 2 smaller molecules, particularly alkyne-related compounds. Up to this point, I think I will call it a day for today. So you have a beautiful day. Thank you so much for listening. Stay safe and healthy. Bye-bye.